This is Bob Capetta, and this lesson is on probability and rules of counting. That is fundamental principle of counting, combinations and permutations. We're going to examine all the possible six-letter arrangements of the letters A, B, C, D, E, F. So in essence, six-letter words with no repeated letters. Every letter has to be used exactly once. And the question we're going to ask is, what is the probability that the letters will be selected in alphabetical order? That means A has to come first, then B, then C, then D, then E, and then F. Well, we have six choices for the first letter. Could be A, B, C, D, E, or F. 5 choices for the second, 4 choices for the third, 3 choices for the fourth, 2 choices for the fifth, 1 choice for the last one. Once we've selected the first 5, there's only one letter to choose from. So what do we have? We have 6 factorial, 6 times 5 times 4 times 3 times 2 times 1 total possible arrangements. That is 6 pick 6, the permutation of 6 with 6 if you'd like. But simpler to think of, I believe, is a factorial. So what is that going to give us? Now we can certainly check that on Excel, right? We could say equals factorial 6 equals FACT 6, and we get 720. So we have 720 possible arrangements. Now how many of those 720 are in alphabetical order? Well, only one. Only A, B, C, D, E, F. So if that's the case, what's our probability of selecting them in alphabetical order? 1 out of 720. That's all we have. All right, let's take a look at another one. Again, 6-letter arrangements of the letters A, B, C, D, E, F. Think of them as words with no repeated letters chosen from that set. And I'm asking, what is the probability the arrangement will begin and end with a vowel? So it begins with either A or E, then a bunch of consonants in the middle, and ends with a vowel. Again, we're not repeating letters. Every letter has to be used exactly once. Well, we've looked at the total possible arrangements in our previous question. 6 choices for the first letter, 5 for the second, 4 for the third, etc. 6 times 5 times 4 times 3 times 2 times 1, or 720 possible arrangements. So we know that. Now the question is, how many of those 720 both begin and end with a vowel? So how many of those 6-letter words begin and end with a vowel? So it's got to go vowel, consonant, 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 vowel. 6 letters. Well, how many vowels do I have to choose from for my first letter? Well, either A or E. So I have 2 letters to choose from for my first position for the first letter in that word. Let's say I choose E. Now there's only 5 letters left. How many of them are consonants? Consonant, 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 consonant. Well, there's 4 consonants, B, C, D, and F. And let's say I choose D. Now I need a consonant again. Well, I've gotten rid of D, so now there's only 3 consonants left. And let's say I choose C. I need another consonant. Now there's only 2 consonants left, either B or F. Let's say I choose F. I need another consonant. Well, there's only 1 left. It's got to be B, only 1 choice. And then finally I need a vowel. Well, I use E in the first slot, so I need an A in the last slot. So this is one example. EDCFBA is one example of a 6-letter arrangement with no repeated letters that both begins and ends with a vowel. Now how many choices do they really have? 2 choices for the first one, then 4 for the second, 3 for the third, 2 for the fourth, 1 for the fifth, 1 for the sixth. That's the number of choices I had to build a word that both begins and ends with a vowel. Again, 2 choices for the first, either A or E, 4 for the first consonant, then 3 for the next consonant, 2 for the next consonant, 1 for the last consonant, and then the last vowel, again, just 1 choice because I used the vowel in the first slot. So 2 times 4 times 3 times 2 times 1 times 1, 8, 24, 48. 48 possible 6-letter words that both begin and end with a vowel. Out of how many total possible arrangements? Out of 720 possible arrangements. And turn that into a decimal, 0.0667. You can reduce that as a fraction too. Not a bad idea. Okay, let's take a look at another question. We're given the following letters, G, 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 E, I, L. So certainly there are repeated letters here. And can you visualize any words that would come from scrambling up those 6 letters, G, 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 E, I, L? Well, I'm going to focus on the word giggle. And the question is, how many distinguishable permutations do I have? So G, 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 E, I, L, and then from that, what is the probability that I would get the word giggle? So we have this bag that has these 6 letters, and I'm going to grab the letters at random. What is the probability that I'm going to get giggle? So I want to look at the number of distinguishable permutations. How many different ways can I set this up? Well, 6 letters total, G, 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 E, I, L, so 6 factorial is going to be the numerator. Now remember, for our distinguishable permutations, I have 3 G's, so I need 3 factorial, 1 E, 1 factorial, 1 I, 1 factorial, 1 L, 1 factorial. So knowing that the denominator, 3 factorial, 1 factorial, 1 factorial, 1 factorial. That's how many different ways we can scramble up the letters G, 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 E, I, L. So on top is 6 factorial, on the bottom 3 factorial, 1 factorial, 1 factorial, 1 factorial. But 1 factorial is just 1. It's not going to add much to the discussion. So 6 factorial, 6, 5, 4, 3, 2, 1. 3 factorial, 3, 2, 1. 1 factorials are all 1. So what does that give us? 3, 2, 1 is just 6. So the 6's would cancel. 5, 4, 3, 2, 1, 20 times 3 is 60, times 2 is 120. So we have 120 different ways to scramble the letters G, 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 E, I, L. And how many of those scramblings are giggle? Well, one of them. That's one of the distinguishable permutations. So our probability of getting the word giggle by grabbing these at random out of the bag is 1 out of 120. Okay, next. 14 men and 16 women work in an office. 8 people must be chosen to attend a conference. If people are chosen at random, what is the probability that exactly 3 men and 5 women will be chosen? So order here doesn't matter. These aren't words. We're not selecting people for offices. You are either going to the conference or not. So the combination is the tool that we want to use here. There are a total of 30 people, 14 men, 16 women, and 8 must be selected. So we're choosing 8 from 30. So if that's the case, the total number of possible groups, sets of people we can choose, will be 30 choose 8. 30 choose 8 will go ahead and give us that number. Now we can look at that formula. 30 choose 8, 30 factorial over 30 minus 8 factorial times 8 factorial. But I can also do that on Excel. So that's combin 30, 8. So if I do that, equals combin 30, 8, what do I get? That number, 5, 8, 5, 2, 9, 2, 5. 30 factorial, 22 factorial, 8 factorial. There it is, 5, 8, 5, 2, 9, 2, 5. That's 30 choose 8. That's the total number of groupings I can have, selected from 30 people, choosing 8 to attend the conference. Now we need to know, in how many of those cases do we have exactly 3 men and exactly 5 women? So that's the question we have to ask next. How do we get that? How do we get exactly 3 men? Well, I have 14 men, we need 3. We have 16 women, we want 5. We know we have this almost 6 million total possible combinations. Again, exactly 3 men and exactly 5 women. 14 men, 3 must be selected. So I have 14 men to choose from, 3 must be selected. So what will that be? There'll be 14 choose 3. I have 364. Again, you could do that on Excel. Just quickly show you that. Combin 14, 3 equals combin 14, comma 3. What do we get? Indeed, 364, which is what I have here. How about the women? We have 16 women. We need to select 5, so there should be more, right? 16 women, I've got to select any group of 5 of those 16 women. I expect that number to be quite a bit larger than 364. So that's 16, choose 5. Let me jump to Excel again. Equals combin 16, comma 5. What do I get? 4,368 here. So 16 choose 5 is 4,368. So the total number of ways I could get exactly 3 men and 5 women would be 14 choose 3 times 16 choose 5. Multiply those together, or 1,589,952. So where do we go with this? That's the number of groups that have exactly 3 men and exactly 5 women. What were our total number of combinations? 5,852,925. So our probability then of getting exactly 3 men and 5 women will be that fraction. Again, doing this on Excel would make a whole lot of sense. We go ahead and get our number of 0.2717. Now, there's an alternate notation that we like. I want to remind you of that because I think this helps with these kinds of problems. N choose R is written with parentheses, an N on top and an R on the bottom. So let's think about what we need here. Our denominator, our bottom part, is 30 people total, and I need to choose 8. So 30 choose 8 is on the bottom. What's on the top? 14 men, I want 3. 14 choose 3. 16 women, I want 5. 16 choose 5. Right? 14 men, I want 3. 16 women, I want 5. Total. What's nice about this notation, you can see 14 plus 16 is 30, and 3 plus 5 is 8. Again, 14 choose 3 times 16 choose 5 divided by 30 choose 8 gives us 0.2717. Take a look at one more question. In the Florida Lotto game, a player must select 6 numbers from among 1 to 53. People get payouts if they select 3, 4, 5, or 6 of those numbers correctly. Determine the probability of selecting 4 of the winning numbers correctly. So exactly 4. That's what we want to talk about. So the probability of getting exactly 4 of the 6 winning numbers. So the way to think of this is there are 53 numbers total. 6 of them are winning numbers, and the rest, the other 47, are losing numbers. So 6 good numbers, 47 bad numbers. We want to select exactly 4 of those winning numbers. We want to select exactly 4 of those good numbers. So how do I want to think about this? There are 6 good numbers. I want 4 of them. There are 47 bad numbers. I want 6 of them. Divided by how many numbers total? Divided by 53 numbers total. And I need to select how many of those? We need to select 6. So again, you can see the advantage of this notation. 6 good numbers, I want 4. 47 bad numbers, I want 2. 6 plus 47, 53. 4 plus 2 is 6. Again, what that means is, of course, 6 choose 4 times 47 choose 2, divided by 53 choose 6. So let's go ahead and do this on Excel. 6 choose 4, 47 choose 2. That's what I need. I need 6 choose 4. I need 47 choose 2. And I need 53 choose 6. This is just text. This is not computation. I just want to make sure I keep everything straight. 6 choose 4, 47 choose 2, 53 choose 6. So we will say equals combin 6 choose 4. Here, boom. Equals combin 47 choose 2. 47 comma 2. Equals combin 53 choose 6. 53 choose 6. And then what's my probability going to be? this number times this number divided by this number equals, using Excel, this number times this number divided by this number. And we get 0.000070631. So what is that? That's a pretty small number. Tenths, hundreds, thousands, 10,000s, so 7 parts in 10,000. Just to kind of give you some perspective on that number, that is in the neighborhood of 1 part out of 1,416. So if 1,416 people played the game, we would expect about 1 person to have exactly 4 of those numbers correct. And that's one of the ways that state lotteries make money, is people assume their probabilities of winning are much higher than they actually are. When we talk about expected value, you'll see how you can determine whether a game is fair or whether it's a good game to play from the perspective of the player. All right, and that will conclude this lesson.